Okay, so think about this. Why does time only ever seem to move forward? And why will a hot cup of coffee always go cold, but you've never seen a cold cup of coffee spontaneously get hot?
Exactly. And how did one of the most brilliant physicists of the 20th century, Enrico Fermi, manage to explain these absolute bedrock rules of our universe with such incredible clarity? A clarity that, honestly, we still rely on today.
To get to the bottom of those questions, we're going to go straight to the source. We're looking at a classic text written by a true master explainer, Enrico Fermi's book, Thermodynamics, which he wrote way back in 1936. And you have to remember the context here. This was a hugely important moment in physics, just a handful of years before Fermi would go on to lead the team that built the world's very first nuclear reactor, literally kicking off the atomic age.
And you know what's so cool is what Fermi says right up front in the book's preface. He basically says his goal was to cut through all the dense, complicated math and just get to the heart of the ideas. His entire mission was about being clear and direct, and that's the spirit we're going to try and capture in this explainer.
Right, so just to be crystal clear, our main source today is Enrico Fermi's Thermodynamics from 1936. As always, you can find the full details for that in the description below.
Now, you can't really get the rules of any game until you understand the playing field, right? Well, Fermi starts his book the exact same way, by making sure we're all on the same page with the basic vocabulary.
Okay, first things first, we have the most essential concept of all, the thermodynamics system. Now, Fermi's official definition is a body of matter which we separate, in theory, from its surroundings by means of a closed surface. I know, that sounds a little formal, a little academic, but the idea behind it is actually super simple.
Yeah, just picture a balloon. The air that's trapped inside, that's your system. The actual rubber of the balloon, that's the boundary, the closed surface. And literally everything else, the room you're in, the building, the entire planet, that's all considered the surroundings. It's really as simple as that.
So once you've defined your system, you have to be able to describe its condition at any given moment. And that's what Fermi calls the state of a system. A great way to think about these variables, temperature, pressure, and volume, is that they're like the system's vital signs. They give you a perfect snapshot of its health, its condition, at one specific point in time. All right, with those basic definitions locked in, we can get to the first major rule of the universe. If you think of reality as this giant, cosmic game, this is rule number one. And it helps to think of it as a really strict form of cosmic accounting.
Which, of course, leads to a question people have been asking forever. Can you get something for nothing? Is it actually possible to create energy just out of thin air? And the first law gives us a very firm, very clear answer. No. It's the principle of the conservation of energy. All it means is that energy can never be created and it can never be destroyed. The total amount of energy in the entire universe is fixed. All you can do is change its form, like from the chemical energy in gasoline to heat, or just move it from one place to another.
Fermi boiled this all down into one beautifully simple equation. Let's go back to that accounting idea. du represents the change in your system's bank account. It's internal energy. dq is like a deposit. That's the heat you add to the system. And dw is a withdrawal. That's the work the system does on its surroundings. And in the universe's accounting system, the books always have to balance. No exception.
Okay, so the first law tells us that the energy books have to balance. That's settled. But it doesn't actually say anything about the direction of those transactions. For that, we have to move on to the second, and you could argue much more profound, law of thermodynamics. This is the one that explains the very flow of time itself.
It's something we see literally everywhere, every single day. Heat always flows from your hot coffee into the cooler room. It never happens the other way around. If you shuffle a deck of cards, they get mixed up. They don't just spontaneously organize themselves back into perfect suits. So why is it that pretty much all natural processes seem to be a one-way street?
Well, the answer comes down to one single, incredibly powerful concept: entropy.
Right, so entropy is often described as a measure of disorder, but it's actually a bit more accurate to think of it as a measure of probability. See, there are just overwhelmingly more ways for things to be messy and disorganized than for them to be perfectly ordered. So the universe, when it's left to its own devices, is always going to drift toward the most probable state, which just happens to be the state of maximum messiness, maximum disorder.
The classic messy room analogy makes this totally clear. A clean room is a low entropy, very ordered state. If you do nothing, just leave it alone, it's naturally going to get messy. It'll move to a high entropy, disordered state. And to reverse that process, to make the room neat again, you have to put energy in from the outside. You have to do work and clean it up. This constant, unstoppable increase in the universe's total entropy is what gives time its direction. It's the arrow of time.
So let's pull all of this together. What's the real legacy of these two simple, elegant laws that Fermi laid out so beautifully? What are the big things we should take away from all this?
It really boils down to three key principles. First, you have to define your system. You can't analyze anything until you draw that imaginary boundary around it. Second, you can't create energy. The first law is basically the universe's balanced budget amendment. There's no such thing as a free lunch. And third, disorder always wins. The second law tells us that the universe's default setting is a relentless, unstoppable march towards messiness.
You know, there's a really great, catchy way to remember this that physicists sometimes use. The first law, you can't win. That means you can't get more energy out of a system than you put into it. The second law, you can't even break even. That's because in any real-world process, some of your useful energy is always going to be lost to increasing the total disorder, the entropy of the universe.
And really, this is the most important point of all. These aren't just some abstract rules for engineers building steam engines. As Fermi showed, these are the fundamental operating instructions for reality itself. They govern every single change that ever happens, from a star burning out in a distant galaxy to the chemical reactions happening inside your own body right now.
Which, when you think about it, leaves us with one last, pretty mind-bending question. If the entire universe is on this irreversible slide towards total disorder, then how on earth do we explain these incredibly complex, highly ordered things, like you and me? What does that tell us about these beautiful but temporary pockets of order that we call life?
So here's a little challenge for you, a call to action. The next time you're with a colleague and they have a cup of coffee, ask them if they can explain why it gets cold using Fermi's laws. It is a fantastic way to make these ideas stick and to share what you've learned. You can talk about the coffee being the system and how the universe is always seeking that equilibrium.
Thanks so much for joining us for this explainer on Fermi's thermodynamics. As always, you can find our full bibliography and a disclaimer right there in the description below.